Welcome dear students. This is a very good problem which demonstrates how a tricky approach can save a lot of time and efforts in physics question. So the question is that a particle of mass m is moving with a velocity v and it enters a stationary object of mass capital M which is free to slide as shown in the figure. All the surfaces are frictionless and the system lies in a horizontal smooth plane. That means you don't need to consider G and all because it is all this whole assembly is lying in a horizontal platform. Okay, so first point, it is horizontal. Second is that it is smooth, there is no friction. This M is free to move any side and this ball is free to move inside the cavity. So you have to find the time taken by the particle to reach from end A to end B. This is end A and this is end B. So this ball will travel from here to here, here, and it will come back. And during this time, this M, capital M, is also sliding in some direction or it is free to move in any direction. So let us see, the cavity radius is capital R. Okay, let us see how to approach this. Suppose this is the situation and the ball has been given some velocity v in this direction. Initial velocity is v. So what do you think? First of all, try to visualize how will the motion look like. Suppose at some instant of time, the ball has reached over here. Then here it will be pushing this bigger block with some normal reaction, let us say n here, and the block will be pushing it back by the same normal reaction. But because of this normal reaction, this mass m will start sliding in some direction. We don't know exact direction where it will. So let us assume that at some point of time, the assembly has reached like this. This is the diameter of the cavity and this is the angular inclination of the ball. So at this instant of time, the ball will be applying a normal reaction, let us say n, on the cavity or the capital M. That means this cavity will also be applying equal and opposite reaction n on the ball. Okay. Now you see, because of this n, this capital M will start moving. I mean, if you imagine the free body diagram, it will be something like this. Normal reaction, normal force appearing. That means n is what? N is ma. Okay, first equation. A is the acceleration of the bigger block. So if you want to analyze the situation from the frame of reference of this block, you will need to apply a pseudo force on this one in the backward direction. So one pseudo force will be acting backward direction. What will be that? Let us call it Fp, pseudo force. And what is the magnitude? Fp is m into a, small m into a, where a is given by this one. So, and if the velocity at this point is what? It is tangential. Let us call v, capital V. This velocity is of small m with respect to this bigger M. So we are analyzing it in the frame. So now the frame has become at rest and pseudo force has come into picture. So if you draw the free body diagram of this ball, then what you will find? You will find this is the ball. It is feeling some force here, what? N plus pseudo force. And in this direction, it is feeling the centrifugal force. What is that? M v square upon r. And velocity is in the direction tangential. This is the direction of velocity. It is perpendicular. Now you see, these two forces are radial, isn't it? These two forces are radial and velocity is tangential. That means no force is there to stop this velocity. No force is acting in this direction. All the force is in radial. So this v will remain the same. This is a very important concept. That means the velocity of the small ball with respect to capital M will remain the same throughout from this point to exit point. It will be traveling with uniform velocity. This is a very important and crucial point here, that this will be traveling with a uniform velocity from here to here. So with this thing in your mind, now you can very easily calculate. You see what is this length? This is L and this is also L. So, and the velocity is uniform. Here what was the entrance velocity? Small v. That means this will remain constant throughout. So time taken will be what? Time taken will be distance upon speed. Distance is what? Distance is 2L plus pi r and speed is what? V. So this is the time which the small ball will take to cross over the cavity. Okay. So I hope it is very clear. And you see, if you had taken the wrong approach, I mean you get lost in this force and direction and velocity, relative velocity, then it could have landed you in trouble. So similarly, let us see the next question. In this question, there is a infinite series of disk, as you can see, and what is happening, there is a plank on the, or the rod you can say, because disk is in 2D, so there is a rod which is lying over on this, and the point over here is that the radius is decreasing. I mean, if this disk is of radius r, then this disk is of radius r by 3, this one r by 9, this one r by 27, and so on. So every time it is becoming 1/3 of the radius of the leftward disk. Okay, and this is the rod, and the mass, I mean the mass of this bigger disk and this rod is same. Okay, so now the question is, you have to find the acceleration of this rod in this direction. So how will approach it? It is infinite. I have not shown everyone, but it is going infinite, something like this. Okay, so let us see how we'll approach this question. Also, there is no friction between the disk, but friction is sufficient between rod and the disk so that the rod is not slipping. It is pure rolling. I mean, this rod is pure rolling on these disks. That means what? You can say that this disk is rolling. All these disks are, I mean, they are rotating, something like this, and this rod is simply, I mean, rolling. There is no friction at this point. Okay, they are not rubbing. So if they are not rubbing, that means energy conservation can be used in this, because there is no loss in friction. So we will be using this approach to solve it. Okay, let us start from here, and you see that the energy, first of all, we will decide that what is exactly happening. Suppose this is the situation, and first of all we need to find this angle theta. Okay, what will it be? Let us say this is the radius r, and the neighboring one is what? R by 3. This will be r by 3. So if you draw a line like this, that means this distance is r by 3. So this one is what? This one is 2r by 3. And if this is 2r by 3, and what is this distance? This distance is the sum of these two radius, that is r plus r by 3. So it is 4r by 3. And obviously this angle is theta only. So here from, in this triangle, you get what? You get sine theta is 1 by 2. First important thing we got. Now, what else we need? Now we need to observe the motion, how the motion is taking place. You see, suppose this rod went down by x distance along this direction, inclined direction. That means how much did the center of mass of the rod go down? Simple, this component of x. That means x sine theta. X sine theta was the loss in the potential energy of the rod. And this, I mean, the loss in potential energy will be what? mg x sine theta. This is the loss in potential energy. And if this is loss in potential energy, it should be the gain in the kinetic energy of the whole system, isn't it? So gain in kinetic energy, how much kinetic energy? Let us say the rod acquired the velocity v. Okay, and all of these, this one will start rotating like this, this one will start rotating like this one will be rotating like this. All the disks will be rotating. Let us say it is rotating with angular velocity omega 1, it is rotating with omega 2, this one omega 3, and so on. Okay, so, and also let us take, for the convenience, let us call its radius as r1, its radius as r2, its radius as r3, and so on. Okay, we know that it is the ratio of 1:3. Radius is decreasing like that. So drop in potential energy should be the gain in kinetic energy. Gain in kinetic energy what? First of all, the K of the rod, that is what? Half mv square. Okay. Second, now sum up all the energies of these disks plus half, what you can say, I1 omega 1 square, I1 omega 1 square plus I2 omega 2 square plus I3 omega 3 square, something like this it will go on, isn't it? something like this. It will go on up to infinity because these are infinite disk. Okay, now you see what there is one important thing is that I1 is what? Suppose we are talking about nth term, we have taken in In will be mn. Mn is the mass of nth disk. Mn Rn square upon 2, isn't it? And omega n will be what? You see from here, every disk will satisfy V is equal to R1 omega 1. Similarly, this disk will satisfy V is equal to R2 omega 2. That means every disk will satisfy V is equal to Rn omega n, isn't it? So you put this value of omega 1 over here. Omega n is what? V upon Rn. So half, I1 omega In omega n square will become what? It will become mn Rn square by 2 times V square upon Rn square. Now Rn square and Rn square cancel and you simply get what? It is mn V square by 2. Okay, so from here if you use this in this equation, you get what? You get, in this equation, let us call this equation A, and we are focusing only on calculating this part because these two are easy. So let us calculate this part. This is what? It is half of, and In omega square you got, so you just calculate it, you will get half of, you can take V square upon 2 outside, V square upon 2 outside, and inside will be what? It will be simple, m1 plus m2 plus m3 and so on up to infinity, isn't it? This term is this term. So now how to find m1? As it is given in the question that the material is the same, let us call the density of the material be rho. Okay, so what is the mass? Mn. Any disk you take, Mn will be what? Rho into V. Rho into V. Volume is what? Pi Rn square times H. H is the width of the thickness of the disk, you can call. Okay, so this is the Mn. Now if you take over here, you put it over here and sum up all that, you got what? You get it V square upon 4 times, now you take rho, pi rho H outside, pi rho H outside, and inside it will be what? Simple, R1 square plus R2 square plus it goes up to infinity. Now if you take, you see here, it is what? It is R1 square is what? R square. R2 square is what? R1 by 3 square, isn't it? Or R by 3, because R1 is R, so we will take it R by 3. And this is what? R by 9 square. So simply it goes on up to infinity. Now what you can do, you take R square common outside, so you get what? Let us see, V square upon 4 rho pi H, so it is V square upon 4 rho pi H R square 1 plus 1 upon 3 square plus 1 upon 9 square and so on, isn't it? 1 plus 1 upon 3 square plus 1 upon 9 square plus 1 upon 27 square and so on up to infinity. So here you see, what is this term? This is nothing but rho pi R square H. This is the mass of the first disk which we have assumed to be n. That means it becomes what? It becomes mv square upon 4 times this GP, isn't it? 1 plus 1 by 3 square plus 1 by 3 raised to power 4 plus 1 by 3 raised to power 6 plus this one up to infinity. So this becomes what? It becomes mv square upon 4 a upon 1 minus r. So 1 upon 1 minus 1 upon 9. That is what? That is mv square upon 4 times 9 upon 8. So our the bigger term, whatever we were needing, that we have got. So now you use this equation, A equation. So these two terms will come up. Mg x sin theta is equal to what? Half mv square plus mgx sin theta is equal to half mv square plus this one mv square upon 4 times 9 upon 8. And you use sin theta equal to half because you see we have already got sin theta is equal to half. So if you put it over there, then you very easily get what? Mg x by 2. Mg x by 2 is what? It is nothing but mv square times 25 upon 32 if you solve it. Okay. Now m and m cancel, and now you differentiate both sides with respect to x. So what you get g by 2 is equal to 2v dv by dx times 25 upon 32. 25 upon 32. That means if you take over here, then what you get, v dv by dx is what? V by dv by dx is nothing but acceleration, and this is what? For it is 8g upon 25. Okay, and this is the acceleration. So our final answer is the 8g upon 25. This is the acceleration of the rod in the sliding direction. So I hope the situation is clear, and if you have any doubts, any confusion, then please feel free to ask in the comment. Thank you.